Okay, can everyone see that okay, or do I need to turn a light down? That's okay, right? I don't know. Probably. Oh, thank you. Yeah, it's perfect. Okay. So the big news is Thursday is test 2. Yep. The only downside of these rooms is like we just have this divider, so like when there's a class next door, we can like hear each other. So you can learn twice as much. So exam 2 is Thursday. And the topics are everything up through, what did we just finish? Newton's laws. So there's no circular motion on this exam. But remember that you are responsible for all the old stuff. So be sure that you refresh your memory on how to do those kind of things. The stuff before the first exam too. Anybody have any questions about exam 2? And then not quite as pressing, but lab exam 2. Is next week in lab. Okay, so that's what's coming up. So what I'm planning to do today is just go back to circular motion and keep working through that. But if anybody has any questions on homework problems or anything related to the exam, I'd be happy to do those. Yes?
Can we go over them?
Which one?
Can we go over them?
Yeah, for sure. Which one?
Both.
What?
Both.
What do you mean?
Like both number 10 and 11?
Oh, yeah, sure. Yep. Nope, I can do that.
That's just strong.
Okay. So this is Newton's laws, numbers 10 and 11. Okay, so first number 10. So I'm going to start, I'm going to choose it doesn't matter which one you choose first, but I'm going to choose the 3 kilogram one as my first body. I just pretty much always just go left to right. So I'll start with a free body diagram of the 3 kilogram. I haven't even looked what we're trying to find yet. The starts of these problems are all the same. I guess the first thing you have to recognize is, does this collection of bodies have the same acceleration or different acceleration? You can see that one's moving up and down and one's moving side to side. So this is different accelerations. And so you have to use that strategy. And so first I'm going to isolate one of these bodies. There's a weight down of 29.43. And then there's a cable force up. Call that T. And Newton's second law says 0T plus 0, negative 29.43 is equal to the mass times the acceleration. Is the acceleration moving along X or along Y? Y, so I'm going to call this 0A.
Why does this one have an A but the elevator does not?
The elevator.
Yeah, remember like back had like questions about elevators and they would have just 0/0.
This one?
Yeah,
Okay, so in this one, you are told what the acceleration is in every one of these. So for part A, it says it's moving with a constant velocity. Remember, constant velocity means zero acceleration. So for part A, you know the acceleration is 0, 0. Okay? For part B, it has an upward acceleration of 2, so you know the acceleration is 0, positive 2. And then downward of, so you know the third one is 0, negative 3. Most of the time in these problems, you don't know you aren't given the acceleration, so that's one of the things you have to calculate. Okay, so the x equation says 0 equals 0. The y equation says t minus 29.43 is equal to 3a. So it's pretty obvious here we're going to be using this one and not the x equation. And like always on these kind of problems, we can't solve this yet because we have two variables in one equation. So now I'm going to go to a free body diagram of the 5 kilogram. And let's see. So the first part of this problem has no friction. The second and third parts have friction. Let's do the one with friction. Is that okay? Because we, because it sort of contains all the stuff in the frictionless part. So let's just do that one to save a little time. So what are the forces acting on this? There's a weight force down of 49.05. There's a cable force here. It's the same cable as the 3 kilograms, so it has the same variable. And now the friction force, let's see. It says the block is yeah, I was just going to look at the direction that they're moving. It says at this instant the 3 kilogram is moving down, which means this block at this instant is sliding to the left. Does everyone see that? And so that means that the friction force is to the right. So there's a normal force here, I'll call that N, and then there's a friction force of 0.5 times N. And now we can go to Newton's second law. 0, negative 49.05 plus negative t0 plus 0.5 n 0 plus 0 n is equal to the mass times the acceleration. And there's one more thing, like to me, this is the trickiest part of these problems where the bodies have different accelerations. So now we have to think of moving the first body we did an inch in its positive direction. How far does the second body move and in what direction? If this one goes, we have it set up as, so like the positive direction as we have it set up, if A is positive, this one would go an inch up. For this to go an inch up, which way would the 5 kilogram cart have to go? Yeah, an inch to the, well, to the right for this one to go up. Do you see that? So it's not a question of what the body is really doing or what the body is really going to do. It just has to do with what you've entered, you know. So, so this is going to be an inch to the right, which is the positive x direction. So I'm going to write this as A0. And we have two equations, negative t plus 0.5n is equal to 5a. And then the x equation, the y equation, sorry, says negative 49.05 plus n is equal to 0. Well, in all these friction problems, you always use the y equation to calculate n and then plug it into the x equation. So this y equation says n is equal to 49.05. And now I'm going to plug that into the x equation. And I get this new equation that says negative t plus 0.5 times what we just found for n, 49.05, is equal to 5a. And I'll simplify that. So negative t plus 24.525 is equal to 5a. And then that's our second equation for our system of equations. And the system of equations we're always going to use to solve for a and t. Okay, well, what can we substitute? This equation up here I can rewrite as t is equal to 3a plus 29.43. And so I'll substitute that into this one. And so I get negative quantity 3a plus 29.43 plus 24.525 is equal to 5a. Any questions about that? And so we get that, so 24.525 minus 29.43. So we have negative 4.905 is equal to 8a. And so a is equal to negative 0.613 meters per second squared. And then if you want the acceleration vector of either one of those bodies, you can plug it into what we have as the acceleration for each one. You know, this is the acceleration for the 3 kilogram. This is the acceleration for the 5 kilogram. Does this ask for a specific one? No. But what you can tell from this is that the hanging mass, since we got a negative acceleration, the hanging mass is accelerating down. And the sliding mass is accelerating, that means to the left. So we can think of it as like this thing is moving, is accelerating this way and this way at 0.613. Okay. And then, all right, well, is that speeding up or slowing down? It's, what?
I was gonna say it depends on the velocity.
Yeah, but and in any friction problem, it did tell you the velocity, that's true. But it says that this thing, what did I say? It's the 3 kilogram is moving down. Okay, so this acceleration is in the same direction as the velocity, and so this is speeding up. Okay?
Are they both speeding up?
Yeah. Yep. Yeah, always on problems like this, if one is speeding up, the other one is speeding up, because the system has that rigid relationship from the string. Yeah.
Why is 0.63 meters per second like not in the negative for those two?
A negative always just reflects a direction, and I just adjusted the directions of the arrows to match that. So what we got, let's take this negative 0.613, put it into the acceleration for the hanging mass. You can see that it's 0, negative 0.613, which is down. So I just drew my arrow down and called it positive. And then also usually you want to calculate the tension. So now that we have this value for A, this variable A, you can plug that into any equation you want to find T. The simplest one would probably be this. So we have T is equal to 3 times negative 0.613 plus 29.43. And so T is 27.59 newtons. Any questions about that? Okay, so the next one is pretty similar, but it has the extra complication of having a rotated coordinate system. Okay, so this, we're given that this angle is 20 degrees. And at the instant shown, again, the hanging mass is moving down, so this is the direction everything is moving. And I guess I'm going to just do it with friction again. So start with one of the bodies. I'm going to choose the one that's to the left, so I'm going to choose the 5 kilogram. One other thing that's important for these is we have one of these bodies that's rolling or sliding on an incline. So for that one, I'm going to use a coordinate system like this. And then we have this other one that's not rolling or sliding on an incline. So for that one, I'm going to use our usual coordinate system. Okay, so a free body diagram of the 5. We have a weight force of 49.05. We have a normal force. And then we have a friction force opposite the direction of motion. So in this case, this friction force is this way. And that's the coefficient times the normal force. And we have to think about the components of that weight force vector. So here's the weight force, has a magnitude of 49.05, and we need to know the angle from the positive x-axis to that weight force vector. So what's that angle? The small angle here is 20. That green angle that we want is 270 minus 20, so 250. Okay, so, so this is 49.05 times the cosine of 250.
So quick question.
Yeah.
So basically you have to like go all the way around until it's like a line down?
You have to go around, it's always the same for finding the components of a vector. You start at the x-axis and go counterclockwise until you hit the vector.
But how do you know what a vector is? Angle stays the same or it goes down? No.
You know where it is because this angle here is always equal to the angle the ramp makes with the horizontal.
So why would it not like go all the way down to like the line where that says 20?
Okay, so why would it not go all the way around to this?
No, so like,
To this?
so it says the line that's 20 if you go up. She's talking about the angle. Yeah.
This?
Up, no. Why would it not go more, basically? Like, you need to scroll the thing up, you scroll up a little bit, you see that it's like on incline, it says like 40% right there. Why would it not go all the way down to there?
Well, what we're trying to figure out is the components of the weight force. So the only thing that we care about is the vector that represents the weight force.
Yeah, that's why I'm asking for all the questions that are like that. Do you basically go all the way until it is a line down with a weight force? Is it
Yeah,
always-
because,
always
yes,
down?
it's
Yeah.
always down because the weight is always
That's
down.
exactly
That's
what I
right.
was asking.
Yeah.
Thank you.
So 49.05 times cosine of 250, 49.05 times the sine of 250. So I got negative 16.78 and negative 46.09. Does it make sense that we got two negative components here? Yeah, because this is in the third quadrant of the coordinate system, so those should both be negative. And now in our coordinate system, is this free to move along the x or y axis? X. And so our acceleration vector is a0. So now I can go to Newton's second law. We have the weight force, negative 16.78, negative 46.09. I forgot the cable in here. There's a cable force. Then there's the friction force. That's in the negative x direction. So negative 0.5 n0. Then the normal force is 0 n. The t force is in the positive x, so t0. And that's equal to the mass, 5, times the acceleration, a0. So we get an x equation that says negative 16.78 minus 0.5 n plus t is equal to 5a. And then the y equation says negative 46.09 plus n is equal to 0. Okay, for any friction thing, just like we did with the last problem, we're going to figure out n from the y equation and then plug it into x. So we get n is equal to 46.09. And then we'll plug that into the x equation. negative 16.78 minus 0.5 times 46.09 plus t is equal to 5a. And I'll rewrite that as negative 39.825 plus t is equal to 5a. And I guess since I know I'm going to be substituting this equation in later, I'm just going to rearrange this now, but you can do that later. So t is equal to 5a plus 39.825. Okay, so now we're done with that first body. The sliding one is the harder one. Now we're going to the easier one, the hanging one. So now, free body diagram of the hanging mass. We have a weight down of 49.05, a cable force up, and it's the same cable, so it gets the same name. And now the acceleration vector for this. Okay, well, if the sliding mass moves an inch in its positive direction, does the hanging mass move up or down?
Yeah.
Down. That's the negative y direction. So this acceleration is going to be 0, negative a. Okay. I mean, in my experience, half the people who lose points on problems like this are going to lose it on this step. So, you know, that can be tricky for sure. But anybody have any questions right now about that?
Did you do the same thing with the other equation?
Did I?
Yeah, did you?
Yeah, I did. The other one I did the hanging mass first, but I said, okay, so our hanging mass, I represented that as, that acceleration as 0a, okay?
So
And so then, yeah, I said, so if a is positive, this moves an inch up. Where would the sliding one have to go for the hanging one to go an inch up? And the answer is the sliding one would have to go to the right. And so in that case, it came out as positive a0, but you have to do that every time.
and then when it's going down,
Negative, yep, exactly. Okay, so now Newton's second law says 0t plus 0, negative 49.05 is equal to the mass times that acceleration we just figured out. And so the x equation says 0 equals 0. The y equation says t minus 49.05 is equal to negative 5a. And now we're just solving that system of two boxed equations. So we get that, what was that? 5a. 5a plus 39.825. That's what the first equation says t is equal to. Minus 49.05 is equal to negative 5a. And so 10a is equal to negative 9.225. And so A is equal to negative 0.92. I think maybe seeing this number, I think maybe a couple people pointed out that I had that positive in my solution. Is that right? Oh, I did it wrong both times? Golly. You'd think I'd have that kind of stuff figured out by now. Okay, so A is positive. So that's the opposite of the answer in my solution, but this is right. And so now you can go back and calculate the acceleration vector of either one of these. What? Okay. We know that A is positive, which means the sliding one is going to be going in the positive x, and the hanging one is going to be going in the negative y. So it's going to be going accelerating this way and this way, 0.92 meters per second squared, 0.92 meters per second squared. And so is this one speeding up or slowing down? I think it said that initially the hanging mass is moving down. That's also the direction of its acceleration, so it's speeding up. And then to calculate t, you can go to whatever equation is simplest. I have it in this form here, so I'll go t is equal to 5 times the acceleration, which we know now, plus 39.825. Yep. And so the tension in that cable is 44.44 newtons. And so if you set up this system with a string that can only support 40 newtons of force, that string will break. If you do it with a string that'll support 45 newtons of force, the string won't break. Any other questions about that one? Okay. Well, let's go through a similar one, and we'll just go step by step, and I'll let you go through it. So let's say, okay, let's do this. This is pretty complicated. I wouldn't do something this complicated on a test, but let's do it here. I think it'll help straighten out some of the issues. Okay, so let's say we have an angle of 30 degrees on one side and an angle of 10 degrees on the other side. And we have a pulley in the middle. On the 30-degree side, let's call that 10 kilograms. And let's make this frictionless, so I'll draw these wheels in here. And then on this side, let's say we have a 20 kilogram. And let's say we want to calculate the acceleration vector of the 10 and the tension in that cable. Okay, so one thing that I want to say before we start doing this is both of these are rolling or sliding on an incline. So we're going to use rotated coordinate systems on both sides. It's going to be this one over here and this one over here. Is everyone good on how I chose the orientations of those coordinate systems? Okay, well, let's start out by isolating the 10 kilogram. And I'll give you a few minutes, see if you can do the free body diagram and come up with Newton's second law for that body. So here's the 10 kilogram cart. The weight force is straight down, that's 98.1. There's a normal force from the ground, I'll call that N10. And a pulling force from the cable. The coordinate system is like this. The weight force is this. And so the angle from the positive x-axis to the weight force is 270 minus 30 degrees in this case, so 240. So it's 98.1 times the cosine of 240, 98.1 times the sine of 240. And so that weight force vector is negative 49.05, negative 84.96. And this is the first body. We can see that this is moving along the x-axis. So our acceleration vector is just going to be A0. And then Newton's second law says negative 49.05, negative 84.96, plus 0 N10, plus T0 is equal to 10 times A0. So the x equation, I guess I'll rearrange it a little, says T is equal to 10A plus 49.05. The y equation says negative 84.96 plus N10 is equal to 0. We want A and T, and so this is the only one that has stuff that we care about. So we'll come back to that x equation. Anybody have any questions about any of those steps? Okay, so the next step is to isolate the 20 kilogram cart. So take a few minutes and see if you can do that. Okay, so this one, the free body looks like this. The weight force is 196.2. There's a normal force, I'll call N20, and a pulling force from the cable that's T, just like the other one was. Here's the coordinate system. Here's the weight force of 196.2. And so what's that angle from the positive x-axis to the weight force? In this case, notice that if you go counterclockwise from the x-axis, you go 90, 180, 270, and you go past that 270 line. So it's going to be 270, right, plus 10 instead of 280 minus 10. So this is going to be 280. So we have 196.2 times the cosine of 280. 196.2 times the sine of 280. And so I got 34.07 negative 193.22. Do the signs of those components make sense with this picture? Yeah, the vector is in the fourth quadrant, so we should have a positive x and a negative y. And now for the acceleration. If this first body moves an inch in its positive direction, that would be up the ramp. Where does this one go? Down the ramp. So is that a positive or a negative x? Positive. Yep. You know, if this goes down the ramp, it's going in the direction of the positive x there. So this is also going to be a0. So now Newton's second law says negative t0 plus 0 n20 plus 34.07 negative 193.22 is equal to the mass, 20, times the acceleration, a0. We have an x equation that says negative t plus 34.07 is equal to 20a. And the y equation says n20 minus 193.22 is equal to 0. We only care about the t's and the a's here, so we're going to keep this one. And so now I'm going to plug this first boxed red equation into the second one. I'm going to replace the t in the second one with 10a plus 49.05. So we have negative quantity 10a plus 49.05 plus 34.07 is equal to 20a. And so we get the negative 14.98 is equal to 30a.
Can you explain how you got there?
Yeah. Where I got which one?
Like that step.
This step. So I have the two boxed equations, and I know I'm okay.
It was just like, how did you go from negative 10a
Oh.
plus 49?
Well, I distributed that negative through here, so we have negative 10a minus 49.05. And then negative 49.05 plus 34.07 is negative 14.98. And I added 10A to both sides.
Yeah, gotcha.
Okay. So A is equal to negative 0.50. We can just plug this into one of those two accelerations to figure out what the system's doing. If I plug that into the first one, I get that it's accelerating in the negative x direction. So this whole system is accelerating this way, and the magnitude of it is 0.5 meters per second squared.
Does that mean it's slowing down?
So on this one, since there was no friction, I didn't have to say anything about what the motion is at this instant, about the velocity. And so if at this instant it was moving to the left, it would be speeding up. If at this instant it was moving to the right, it would be slowing down, but we don't have that information. If there's friction in the problem, I have to tell you that, otherwise you don't know which direction the friction force is acting. But on ones like this, I usually don't. And then the last step is almost always calculate that cable tension. So I'll use this form. T is equal to 10A plus 49.05. So T is equal to 10 times what we got for A, which is negative 0.50, plus 49.05. And so that cable tension is 44.05. Any questions about that? Okay, let's do one more. We'll just finish up with stuff that's going to be on the test, and then next Tuesday we'll go back to circular motion. Okay, so let's say we have a ramp at an angle of 20 degrees. And two carts connected by a cable. Let's say the one on the left here is 2 kilograms. The one on the right is 3 kilograms. And let's say we're pulling on it with a 30 Newton force. And we want to know what's the tension in the cable. There could conceivably be two cables in this question. Like to pull on this, you're probably pulling on some kind of cable. But this one, we already know the tension is 30, so there's not really any like ambiguity about what I'm asking here. This is the only one we don't know. Okay. So if all we're trying to do is calculate the tension in the cable, what's the first step for a problem like this? Yeah, okay, so always free body diagram, but what do we want to isolate for the free body diagram? What? The total, exactly. So do the first step and see if you can, so isolate the whole system together and see if you can calculate the acceleration vector of these carts. Part to calculate that acceleration vector A free body diagram looks like this. We have the weight force acting down. This whole system has a mass of 5 kilograms, so the weight is 49.05. There's a pushing force. I'll call that N total. And then there's a cable force of 30 newtons. And that's all the contact. For the weight force, there's the coordinate system. The angle from the positive x-axis to the weight force, in this case, is 270 minus 20. So this weight force is 49.05 times the cosine of 250, and then 49.05 times the sine of 250. And that is, well, we already had that one today, I think, negative 16.78, negative 46.09. And then the acceleration, we're just going to call, this is free to move along the x-axis. So the acceleration, we're just going to call A0. And then Newton's second law says negative 16.78, negative 46.09, plus 0 in total. Plus 30, 0 is equal to the total mass times A0. The X equation says negative 16.78 plus 30 is equal to 5A. So A is equal to positive 2.64 meters per second squared. So plug that back into the acceleration vector here. And you get that the acceleration vector is 2.640. Okay, so the next step is, now that we have the acceleration vector, we're going to isolate one of those two carts. Bless you. Which one of these two carts do you want to isolate? So no matter which you choose, it's perfectly fine. You'll get the same answer either way. I guess there's a little less going on with the 2, so maybe the 2. But if you want, some people try isolating the 3 kilogram, and what you'll see is that T comes out the same. So I guess what I'm going to do is isolate the 2 kilogram. So take a couple minutes. We don't have a ton of time left, but take a couple minutes and see if you can calculate that force T. Just before we run out of time. So I'm going to isolate the 2 kilogram. There's a weight force down of 19.62.
I should have this.
And a normal force I'll call N2. And then the only other force is that cable force.
Oh yeah, I'll do that. Yeah.
Our coordinate system is like this. And so we're going to use that same 250-degree angle as before. So we have 19.62 times cosine of 250. 19.62 times sine of 250. So the weight force comes out to be negative 6.71, negative 18.44. And so Newton's second law says negative 6.71, negative 18.44 plus 0 n2 plus t0 is equal to 2 times the acceleration vector we got before, 2.640. And so the x equation says negative 6.71 plus t is equal to 5.28. And so t is equal to, what's that? 11.99, yeah. Anybody have any questions about that?
I got it right.
Woo! All right, bye. So get ready for the test on Thursday.
Oh gosh.